So, in this video we will see certain properties of Fourier transforms of a periodic function. Before we do that, I will just have a recap of what we have done last video. You have seen what is the Gibbs phenomena. What you have seen is peak, the first peak, when you consider when you try to estimate the Fourier series with few terms. What you see is there is an artifact coming into picture. So, there is a first peak, as many terms, so whatever may be your number of terms in your Fourier series, but that first peak around that discontinuous point, either sides, you will have a peak, and you calculate the value of that peak, and what you see is this Sk. So, this Sk, this is the partial sums. If you take k terms and L by 4k, that is where you have the peak, Sk of L by 4k, that is the value of the peak. So, that is what we have seen, that if this is a half, this is your this thing. So, you get something like this. If you increase the number of terms, these things slowly vanish. So, what you see is, you will now see that C is going to be valid. So, as you increase k, go bigger and bigger, if you increase further, what you see is only still the peak will be there, and this width of this first peak, that is going to be very, very small. So, very narrow, but the area, but the peak, the value of the peak will be always, there will always be some peak. So, as you increase, so as you see mathematically, as k goes to infinity, this limit is obviously this more than 0.589, but the actual value should be, as k goes to infinity. So, they increase the number of terms, you take the infinitely many terms in your Fourier series, then only it will converge to the actual value. That is what the theorem says. Okay. At discontinuous point, a theorem says if you take only infinitely many terms, full Fourier series, when you consider, then that converges to pointwise. So, at a discontinuous point, it is the average value of function. So, in this case, in this example, the average value is minus half and plus half, that is 0 divided by 2. So, it is 0. But here whatever, so you cannot take infinitely many values. So, this k goes to infinity means k is bigger. So, it is never going to be infinity. So, you are not considering all the terms in your Fourier series. So, some big value, there will always be a peak. Okay. So, that peak value is more than 0.5. So, you have a 9% overshoot. There will always be overshoot at a discontinuous point. That is what you call. So, if this is what is discontinuous, jump discontinuity here. So, there will always be a overshoot of your Fourier series. Okay. So, at this point, eventually you will always see, if I remove this, you will understand. So if I take really big number of terms, many number of terms, if you consider, what you see is exactly matching. Somewhere here the small is going to be, there is a small, it is like this. So, there is always be overshoot either here or here. So, that is what is called Gibbs phenomena. That is what we have seen in the last video. So, this is a kind of artifact you see in the Fourier series if you try to estimate with the finite number of terms of your Fourier series. So, if you want really exact value at a discontinuous point, it is only theoretically possible, as you have to consider infinitely many terms from the Fourier series. So, that means that converges to the average value of the jump. That is what theorem says. That is the, so if you try to estimate from the Fourier series, you have to consider only finitely many terms, however big it may be, number of terms, but you will always have a overshoot value at the discontinuous point. That is what is the Gibbs phenomena. It is not really important, it does not have any impact on the Fourier series. Just want to give you what happens, what is the Gibbs phenomena by considering trying to estimate from the Fourier series of the function. So, kind of reconstructing the function from the Fourier series if you try to do. So, it is not possible at discontinuous points because there will always be an artifact. For example, here is always 9% error, and if you consider different example, you may have a different error. So, but that error is always fixed, whatever may be number of terms is always. So, this will always be minimum of that error will always be there. That is what I want to convey from this Gibbs phenomena. So, we have seen what is Fourier coefficients are also called we call them Fourier transform, and Fourier series is also called inverse Fourier transform. Fourier series or inverse Fourier transform, inverse Fourier transform. So, if you call this Fourier transform, this is inverse Fourier transform. If you call this Fourier coefficient, then what you get is you get back your signal by Fourier series. So, kind of transforming and then you come back, that is an inverse transform. So, you try to see now certain properties of this definition, some properties of Fourier transform. So, first one is linear property as usual. So, we will see even when you define Fourier transform over a full real line, Laplace transform and Z transform, what you see certain properties of these transforms. Okay, it is a mapping from functions to function space. So, you are actually defining. So, if you look at this cap is the operator acting on the function f, what you end up is finally function of so you integral is a value, so that depends only on n. So, you take the functions f of x in some function space to some number f cap n. So, some discrete sequence, basically you get a discrete sequence of numbers. That is what is the Fourier transform of a periodic signal. Okay, Fourier transform of periodic function. So, even if you define it over full real line, so you take fx and what you end up is here for each n, for each f you have for different n values you have this f cap of n. So, there is a sequence of numbers, n is running from n belongs to z. Okay, that is what it means. So, look at the first property, that is called a linear property. So, what it tells you is that you consider instead of this function f, if you consider some c constant times f1 plus f2 of x. So, you consider this function. For this you consider the transform of this is the meaning. This is of this n is equal to c times f1 cap of n plus f2 cap of n. So, this is what is the results is always linear. This cap, that is the Fourier transform. If you take combination of two functions with the coefficient, the coefficients comes out and this is just a linear. So, cap you can linearly distribute it. So, this is you can easily see this just by the definition. LHS left hand side, if you consider what is this one. So, by definition this is going to be 1 by L minus L by 2 to L by 2. Now, instead of this function f you have c times f1 x plus f2 x times e power minus I n omega naught x dx. Now, what is this one? So, because it is a linear function, so that is clear, right. So, this is 1 by L minus L by 2 to L by 2 f1 of x e power minus I n omega naught x dx. You can split this integral into two parts. One is constant, other one is 1 by L integral minus L by 2 to L by 2 f2 of x e power minus I n omega naught x dx. Of course, you have to consider all the functions combination f1 f2 are both functions with period L, then this the transform will be definition is Fourier transform is this, and this is nothing but a c times this is exactly Fourier transform of f1 cap of n plus this is f2 cap of n. So, this is exactly your RHS. So, this is obviously this is true. A second property that we have is we will just consider f of x. You take a signal, you take this signal can be even complex valued. So, take its conjugate and you have a conjugate function. So, as some g of x, for which if you take the Fourier transform is a function of n, and that should be equal to f cap of minus n, and then you take a conjugate for that. It is a complex number on which you have to take a conjugation. So, this is also true. So, again you start with LHS 1 by L minus L by 2 to L by 2 f x bar into e power minus I n omega naught x dx. So, at the right hand side you have a bar comes up. So, you try to take the full bar outside. L is a constant real number. So, minus L by 2 to L by 2. So, when you take the full bar, so what happens when you take the full bar? So, this is f x, and then you have when you take this bar. So, this when you take the bar, when you take the bar, so you have f x gx dx, for example. For this bar is actually integral f x bar gx bar dx. That is what it means, because if it is over a real interval, I belongs to I is a real interval. So, this is what is the case. So, using this you can write f x, and this e power minus I when you take the conjugate, because bar you are imposing bar. So, you have 2 bars, right? You have 2 bars, and what you have is this e power minus I n omega naught x dx. Now, first this bar you try to put it here, bar goes, and this bar over this, and dx is as such. So, here but because of this you have plus. So, you have this one. So, this is exactly equal to, this is f n f of f cap of minus n for this whole bar. So, this is exactly your right hand side. So, these are trivial properties which you can see sometimes it will be useful. Okay. So, we will just do it. It is called conjugation, linearity. First one is called linearity, a linear property. This is called conjugation. So, if you shift in time, so time variable we are considering as x. If you shift in time, and also so what is the effect in the Fourier transform, that you can see that f of x minus x naught, you shift with x naught, okay, and then for this if you take the Fourier transform, this is exactly equal to what comes out is exponential term. So, I n omega naught x naught, and you have f cap of n. So, this is shift in time, shift in time. So, time is the x variable here. So, x is time. So, again, so LHS proof is easy, that is why I am just doing it here itself by considering LHS equal to RHS. 1 by L by definition, this cap means the definition minus L by 2 to L by 2 f of x minus x naught e power minus I n omega naught x dx. This is equal to 1 by L. So, now what you do is you consider x minus x naught equal to t. 1 by L, if you consider x minus x naught, if you put x minus x naught equal to t, so dx equal to dt. So, you have dt f of t e power minus I n omega naught, x is x naught plus t. Okay. And what happens to your limits? Limits will be when you put x equal to minus L by 2 minus x naught, that is your t, L by 2 minus x naught. Because it is a periodic function f, it's and also exponential function is also periodic. Okay. So, the integrand is periodic, so that implies with period L. So, this is this is also having a period L. So, as you have already seen earlier. So, it is the same as considering L by 2 to L by 2 is same as you consider minus L by 2 plus some x naught. This is the length of x naught. This to the same length you go out. So this is same. The same values will be repeated here. So this is because of periodicity, you can replace this as minus L by 2 to L by 2. So this is exactly, so you remove this e power minus I n omega naught x naught, because the constant that comes out, what is left is simply f cap of n. This is your Hs. That is the third property, and we have the fourth one, that is time reversal. You can just go back, time reversal property. There is f of, you can go back to the time. So minus x for this cap. If you take the transform, what is the result? So this is f cap of minus n. F cap of minus n. So this is called time reversal. This is called time reversal property. This is also easy to show. So I would consider LHS 1 by L minus L by 2 to L by 2, f of minus x now, and e power minus I n omega naught x dx, and you want the Fourier transform of f. Okay, so f of x basically. So that means you put minus x equal to t. So that will give you minus L by 2 to L by 2 minus L by 2, because after substituting the limits, and f of t e power plus. E power plus is minus of I n omega naught t, okay, that is t, and dx is dt minus dt. So that makes it this, if you remove minus, this you can replace, you can interchange the limits. That's what it is. So you have minus L by 2 to L by 2. This is exactly your f cap at minus n. You need minus of minus n, that is, so you have minus n. This is your RHS. So you can easily see these properties. The simple properties. If you are working, if you are doing algebra with these transforms, with the signals, you can will be useful. And some other properties, non-trivial properties, not so easy properties, are these. If I define, you take the product of two signals. So if you take two smooth signals, so let f of x and g of x be two piecewise smooth. Smooth means smooth functions. What is a smooth function? We define what is called piecewise differentiable function. So piecewise differentiable function means f is piecewise differentiable. Piecewise differentiable function means f dash is piecewise continuous, and you take any n derivatives if piecewise differential for every n. That means any n plus 1th derivative is piecewise continuous, right? So if f of nth derivative of fn is a piecewise differentiable function for every n, then f is piecewise smooth function. Piecewise smooth function. Okay. So that means you take next derivative, that is piecewise continuous function. So this is true for every n. So then you say that it is piecewise smooth function. So such a piecewise smooth functions. All the examples that we consider with elementary functions, for example this one, this is derivative is 0 here, but it is not defined at this point 0. So except at that point is 0 function. So again next level, what is that? Except that point 0 only, again it is differentiable any number of times. Similarly, you consider this and this, anything with the elementary functions. If you represent your signal, there is actually piecewise smooth function. if you such thing if you have, then h of x that is and let h of x equal to fx into gx. Take the product of that, then h cap of x, h cap of n, that is f into g of x. For this you take the Fourier transform of x of n. Okay, this should be equal to you get a series k is from minus infinity to infinity, and you have f cap of k into g cap of n minus k. That is what is the result. So, this you can prove by simply considering the left hand side again. This will be 1 by L integral minus L by 2 to L by 2. They are all piecewise smooth functions, smooth periodic functions. Okay, periodic functions with period L is standard. Okay, so without do not mention, unless we mention it, it is always periodic function with period L. So, this into h of x, that is fx into gx into e power minus I n omega naught x dx. Okay. Now, what you do is, so you have, because f is a piecewise smooth function, piecewise differentiable function, and you have a Fourier series for f. So, let me write this Fourier series minus L by 2 to L by 2. Fx, I have a Fourier series, that is n is from minus infinity. So, k is from minus infinity to infinity. For fx is sigma, k is from minus infinity to infinity, f cap of k into e power I k omega naught x. This is your fx into gx e power minus I n omega naught x dx. I just substituted what is f. You can also substitute for g, you will have a different thing. So, f and g can be interchanged in this summation. If you replace g as a Fourier series, you will get f and g are interchanged in this final result. Okay. So, we will see what you get. So, what is the next thing is, I will take this, I will bring this summation, or rather I take this integral inside this infinite series. When is this possible? It's you can do you can do this Fourier series. You can do or any series for that matter, any function series f n of fk, let us say fk of x, and k is running from minus infinity to infinity. If you have an integral, this is same as k is from minus infinity to infinity integral fk of x. This is questionable. If it is a finite sum, this is always true, because it is infinite sum. When you can do this, if this series converges uniformly, then you can do this. Okay. If this series is converging, that means you take the partial sums of this series, that is k is from minus n to n f k of x. If this converges to some function, this actually converges to the series as a sequence, this converges to f k of x. This sequence of functions, if you call this S n of x, and this is your S of x, and this S n as a sequence of functions, this converges to S x uniformly. Then you can do this. What is the meaning of uniformity? Means this converges, you give an epsilon, so that means it does not depend on the domain. So, that means if you know the definition of convergence, basically this is essence will be close to Sx. How close? Let me put some however small number, you give your epsilon, there exists some number n beyond which some number big N, okay, for some n. For some n, this is the meaning, you fix x, Snx converges to Sx, okay, pointwise, that is pointwise because you are fixing x. So, given epsilon, if I give epsilon, there is a n for some n that depends on epsilon and also x, because the fix it depends on x. Every time you change your x value, there will be different n that depends on epsilon and not only epsilon but also on x. If you can get some n that depends only on epsilon, that means independent of x, it works for all there is a n that works for every for some n that depends only on epsilon, that means it works for every x in the domain, okay. X belongs to actually here minus L by 2 to L by 2. So, if that is true, then it is called this uniformly convergence, okay. So, you have the Fourier series, basically what is this, what you have is a Fourier series, including the Fourier series f cap of k into e power I k, this is a constant times e power I k omega naught x, that is a function, gx function, and this is another function. So, you have this is your function, is a function series, that is your fk. Your fk is actually a complete whatever is inside here, okay. So, this integral dx is same as integral, so that is what it means. So, why is this convergence? So, Fourier series, if it is uniformly if it is a piecewise smooth function, it is uniformly convergent, one can show, okay. Can we show that one? Can we show that Fourier series is converging uniformly? Yeah, so we will show this series how it is uniformly convergent. If you look at the Weierstrass test, Weierstrass M test, Weierstrass M test, if you know a Weierstrass M test, that tells you that this sum in this series, this part f cap of k, there is a constant, and e power I k omega naught x gx and e power minus I n omega naught x, this summation k is from minus infinity to infinity, and if you apply this M test, each of this part, if this is less than or equal to f cap of k into g of x modulus of this, okay. Now, since g is integrable, piecewise periodic smooth function, piecewise smooth periodic function. So, you have this is obviously bigger than f cap of k into this integral g of x as L by 2 to L by 2 dx. This is anyway finite, this is the finite quantity. So, this is something like some, because g is piecewise smooth. So, m times f cap of k, okay. So, this is what it means. Now, this series is always finite for every x if this series is finite. If you know that this series is finite, that is by M test. So, since sigma f cap of k, this series k is from minus infinity to infinity, this should be finite. Do we know this one? If this is true, then we can say that this is true, this is finite for every x, that means it is uniformly convergent. So, you can do this integral, you can take it inside this sum, that is what it means. So, let us not get into this. So, assume that this integral we will try to justify later. So, as of now, so let us assume for some reason. So, what is given information is that f and g be piecewise smooth periodic function. So, the product is also piecewise smooth periodic function. So, it is obviously it is absolutely integrable. So, f is a piecewise integral means it is obviously what we know, this information is minus L by 2 L by 2 mod f of x is finite, dx is finite, and also gx implies the product is also mod fx into mod gx dx is also finite. This is what is given information. So, using this one can actually show that this this series converges uniformly. So, through M test or by some other means we will see later. Okay. So, this is one way of showing that uniform convergence. So, let me not dwell on this. So, assume that you can do that, this is possible to do. So, you can take this inside and then what you get is then we get k is from minus infinity to infinity f cap of k. So, what is left is what is left with is 1 by L minus L by 2 to L by 2 g of x e power I minus I n minus k omega naught x dx. So, this is exactly equal to k is from minus infinity to infinity f cap of k into this is nothing but g cap of at minus n minus k at n minus k. So, this is exactly your RH right hand side. Okay. So, somewhere you have to justify that this series is uniformly convergent. Okay. So, what is given information is that if f of f product the product function mod h of x, okay, this is absolutely integrable function, f into g is absolutely integrable function. So, that implies you can see that it is going to be uniformly convergent. That is clear, right. So, and you can why is this so? That is not difficult to see because yeah. So, I think it's easy. So, how we justify this? We justify this step, okay, by showing that this series is uniformly convergent. So, how do I do it? I consider fx into gx, okay, modulus of this, okay, this is less than or equal to fx gx, no wait, we consider this k is from minus infinity to infinity f cap of k into e power into g of x e power I minus I n minus k w naught x. This is what this series, which is equal to fx gx into e power minus I n omega naught x. Okay. So, this is exactly same as this one, this integrand. Each of this term when you take with modulus f cap of k into g of x modulus, exponential modulus is 1, is obviously less than or equal to, it should be less than or equal to this modulus, that is fx into g of x. This modulus is 1, right. So, the integrand is this, this will be less than or equal to. So, let us assume this result. Let's try to we will try to justify this later. Okay. So, I think I am not getting exactly, but somewhere you have to use, if because of this integrability of the product of this function, we will see that we can show that this series is convergent. That implies you can take this integral inside this sum, that will give this right hand side. So, let us move on. So, I will try to justify this in the next video. So, we will see some other property, another non-trivial property that we have is a convolution of two functions. If you have two functions fx and gx, you can convolve them. This is the notation for this, that is you just that is some integral of, that is this is the definition of this, L by 2 to L by 2 over the same integral. So, these are periodic function with period L. So, that is minus L by 2 to L by 2. So, you convolve with, convolving means you consider f of t into product of g x minus t dt, and then you take the integration. So, that is like if you want it function something like this is your f of x, and f of g is another function, and what you do is you just translate g of with g of x minus 2, for example. This one, this is f of x. The convolution is the product at like this, the product of this that will give, and you integrate. Once you take the consider the product and you integrate, and what you end up is the convolution f cross g at the value 2. Okay, that's what it means. Or 2 minus x, you can say, you should consider like this. Then that is called this is convolution value at 2. So like that you consider for every x. So for every t, so you consider always t minus x, 2 functions you consider. So such is the definition of a convolution. So convolution of 2 functions. So because the f and g are f and g product is this product, they are periodic functions and their product is integrable, square integral, they are absolutely integrable functions. Because of that, this is always finite. So this is well defined, because this integral, this modulus of this is less than or equal to modulus of less than or equal to integral modulus of this. That means, and which is finite. So that means this is well defined function. Okay, so this is well defined. This is a convolution of product of 2 functions, convolution product of 2 functions f and g. So if I consider them as piecewise smooth periodic functions, their product is well defined because this integral is finite in that case. Then what is this one? What I have is then f convolving g, the convolving function, this is the convolution function is f convolving g of x together is also periodic function. Then is a periodic function, is also periodic. If f and g are periodic, this is also periodic. So how do we prove this? You consider same period. So you consider x plus L, and you simply write or the definition minus L by 2 to L by 2 f of t g of x plus L minus t dt. So just by change of variable, you can see that because it's a periodic, f and g are periodic functions, the integral will not change, integrand will not, this limits will not change, though they actually change, and this is actually same as again that is equal to the same minus L by 2 to L by 2 f of t. So what you do is x plus L you take it as x1 x dash, then rather what you do, no, so it's not straightforward, you don't have to do anything. So don't do anything. So simply g, since g is periodic with period L, this is exactly g of x minus t dt. So this is nothing but your f convolution of g at x, that is your, so that means it's periodic function. 7th again on convolutions, and if you consider 2 such periodic smooth periodic functions, piecewise smooth periodic functions, you convolve these 2 functions and you consider the Fourier transform of that, you get that as f cap of n into g cap of n. So the way we defined as this convolution, this constant term, so this is in your hands. So if you change, you may end up, this relation will also change. If you try to change your definition here, and this result will change. Okay, so we will see exactly whether by defining 1 by L, that factor, we will get this equal or not. Okay, or we may get some other constant here. So let us see what it is. So LHS is 1 by L of minus L by 2 to L by 2 f convolution of g of x into e power minus I n omega naught x dx. That is my LHS. And now 1 by L square minus L by 2 to L by 2 f composition of g now 1 by L that comes out, that is L square, again minus L by 2 to L by 2. This is now convolution f of t g of x minus t dt into e power minus I n omega naught x dx. So, this is equal to 1 by L square minus L by 2 to L by 2, one more integral L by 2 to L by 2, f of t. What you do is I try to replace x minus t as x1. So, you have g of x1. So, I try to change. So, what happens if I replace this with the outer integral? So, that is dx integral. So, you have dx equal to dx1. So, I have dx1 and this limits will become, when you put x equal to minus L by 2 minus t plus L by 2 minus t. So, outer will be minus t, and this, because they are periodic, they are same as minus L by 2 to L by 2. So, they do not change. So, and you have this, and dt is as it is, and this is e power minus I n w naught, x is now x1 plus t. So, dx. So, now these are separated. Now, these are the two integrals, 1 by L integral minus L by 2 to L by 2 f of t. So, t integral you can write separately. Now, they are separated. This integrand is two separable functions, f t e power minus I n omega naught t dt into 1 by L minus L by 2 to L by 2. Now, this is now g of x1 is a dummy variable. So, you can write again dt, you can write if you want as gx1 e power minus I n omega naught x1 dx1. So, you can see that these are same. So, these are Fourier transform of f at n and g Fourier transform of g at n. So, this is exactly. So, if you define it like for this function composition, that is convolution of two functions. So, in fact, you do not need really piecewise smooth functions. You simply consider, as long as they are well defined, the the convolution product is well defined between two functions, the Fourier transform will always give you, of course, you take the periodic functions. Periodic functions, if you consider, you always see that the convolution, Fourier transform of convolution will be product of the Fourier transforms. So, this is the property, important property. So, now you have one important last property which you have, and we will see this in the next video. What we see is so far we will just giving you some kind of properties of these transforms. That will be, so similar properties we will be doing for other transforms in the later videos. So, these are very important properties, sometimes may be useful. So, just they are simply simple application of known results in calculus, and we have one more simple property that along with that, and we will give the recap of what we have done, and we also give some result on delta functions which are useful. One simple result that will be useful. So, we have seen that delta function, we have defined what is delta function. We have seen that by definition integral of the delta function over the full real line minus infinity to infinity is 1, and if you actually consider only between 0 to infinity of delta function delta x dx, and it should be half. Why is it so? We will see in the next video, along with a recap of what we have done for the Fourier transform of a periodic signal and its inverse transform or Fourier series of the periodic function or signal. Okay. So, we will see this, we will have a recap of everything what we have done. Final example we will see, we will recap, and then we will do some more examples. We will try to do some more example in the next video. Thank you very much.